All right, so not only do molecules have to hit each other in the correct orientation, they have to hit each other hard enough to react. So they have to hit with enough energy to actually react. This energy required is what's known as the activation energy. And it gets the symbol E sub A. And so to fully understand this, we need to draw some reaction coordinate diagrams. You've probably seen these in Chem 101, but we're going to kind of fill them in a little bit more. So we're going to take a look at an example of compound AB. Say A is bound to B. We're going to add C to it, and then we're going to form AC plus B, right? So C is taking the place of B. And we'll envision it as an exothermic and an endothermic reaction. So let's go ahead and just draw one of our reaction coordinate diagrams here. So we've got energy here, and then we've just got reaction or reaction coordinate down on the bottom. So on the left side will be the reactants, and on the right side will be the products. On this case, we're going to take a look at endothermic. So think about endothermic. What does that mean? It means that the system is absorbing energy, so your reactants are going to be higher in energy than your products. So that means that we have to draw our reactants down here, and then our products somewhere above it, right? So up here we have AB, and then C by itself, and at the end we end up with AC and B by itself. And so this gap between the two is your enthalpy, so your delta H, right? We see it's positive here, so it's an endothermic reaction. However, a reaction cannot just go kind of in this linear fashion. Instead, it has to go over a hump, right? So it's got to actually have more energy in it than the final product. And the distance from our reactants to the top of this hump is our activation energy. Put this in a different color. Activation energy. And then on top of here is what we have is what's known as a transition state. So it gets this little brackets, and then it gets this equal sign with this kind of cross going through it. And so that's the transition state. The transition state is what the molecule looks like in between the product and the reactant. One important thing to know, though, is that you cannot isolate a transition state. It's fleeting, it's intermediate, it is not stable, and so you cannot isolate it. So that shows up what an endothermic reaction looks like. Let's check out an exothermic reaction. It is slightly different. So we'll have energy here, reaction. We're going to call this one exothermic. And so our reactants will be higher in energy than our products because we're losing energy. So up here we have A, B, and C, and then here we have A, C, and B. Again, the difference in between the two gaps, or the product and the reactant, is our delta H, our enthalpy of reaction. But again, our product cannot just go down a hill like this. It must overcome a barrier. It must go over a hump. So that'll look something like that. And then now our activation energy is not this whole distance, but it's only from the reactants to the top of the hump. So this is our activation energy here. And then of course we have a transition state, and we can envision maybe what this transition state looks like, right? We're breaking an A-B bond and forming an A-C bond. So maybe it looks something like this, right? Where these dots represent a bond forming and a bond breaking, right? A is slamming into C to form a bond with it while simultaneously breaking its bond with B. So be able to draw these reaction coordinate diagrams, be able to kind of just be comfortable with them. The main key that you want to kind of really focus on here is the bigger the activation energy, the slower the reaction. And we'll take a look at that in detail later on. So let's just rewrite this again. Activation energy, remember it's from the reactants to the transition state, or the top of the hump. The transition state is a local maxima, right? It's the maximum hump. It's up there. You cannot isolate. It is fleeing. It is not stable. You cannot isolate it. And then we have our change in enthalpy, our delta H. This is the energy difference from reactants to products. And so here, this picture is just demonstrating the same thing, right? Exothermic reaction. In this case, we're going from this CH3 connected to the N of this cyanide to the C of the cyanide. And you can see the kind of the transition state is kind of in between where this part of the molecule is rotating.